Hi everyone, Assalamu alaikum. I hope you're all doing well. In this video, we'll cover the Chemistry Unit 5 predictions for the January 2025 exam. With your exam just around the corner, I've selected key questions that are highly likely to appear. This will help you practice effectively and boost your confidence. Stick around until the end of the video where I'll share a list of frequently asked questions from past 4 to 5 years. These frequently asked questions could get you 7 to 10 marks in your exam. Inshallah. Let's get started and make the most of this session. So we start off with this question about electrode potentials. So this question says that some standard electrode potentials are shown in this table, and then which of these ions is most likely to catalyze the reaction between S2O8 2- and I-. Okay, we can see here that the most likely catalyst is a positive ion, obviously, because since these two ions are negative, this won't react with each other, since they will have a really high, very high activation energy, since they both are negative ions, and then negative ions repel each other, right? So we need a positive ion for them to be catalyzed, for the activation energy to be lowered. So Cl- is eliminated by that choice. So we're left with 3 positive ions. Now Fe2+ is our prime choice, because if you look at the reduction potential for Fe2+, it's plus 0.77. Now if you look at the reactions, so Fe3+ or Fe2+ will react with S2O8 2- at first. So this reaction proceeds, and this reaction's E cell is 2.01 minus 0.77, since S2O8 2- is being reduced and Fe2+ is being oxidized. So this gives a positive value, which is a feasible value. Therefore, the reaction proceeds. And similarly, since after this reaction, Fe3+ is formed, this Fe3+ then reacts with the I-. So Fe3+ now is being reduced and I- is being oxidized. So 0.77 minus 0.54 gives us again a positive value. That means the reaction is feasible. So since both the reactions is feasible, and by the end of the reaction Fe2+ is reformed, therefore our prime catalyst is Fe2+. This kind of question comes often in the question paper, so also be sure to study on the electrode potentials and how E cell is found out. So E cell equation is E cell, to find E cell, to reduction minus oxidation, right? Remember this equation, since you will need this. Okay, moving on to the next question. This question says one of the monomers used to make PET is benzene 1,4-dicarboxylic acid. So this is the displayed formula. Now, how many peaks are there in the carbon 13 NMR spectrum for benzene? Okay, so we need to find out the different carbon environments, right? So in this is a symmetrical compound, right? This is a symmetrical compound. So from this axis, this is a totally symmetric compound. Therefore, if we count any one of the carbon atoms here, we don't need to count any carbon atoms from this side, because they both will have the same environment, right? So here you can see that this carbon here has a different environment, and this carbon too is different from this carbon. Therefore, it will give 2 separate peaks. And similarly, this carbon here is in a different environment, so this carbon will also give a different peak. But if you consider this carbon is the same as this carbon, right? This carbon, so if we say this is 1, 2, and 3, so this carbon is in a similar environment as carbon 3. Therefore, they will give the same peaks. So in total, we have 3 different carbons that are in 3 different environments. Therefore, there will be 3 peaks. Now, this is a very common question that comes: which of these is the weakest base? This question can be in various forms, but you just have to understand the concept of this. So here we have 4 options: ammonia, then we have butylamine, which is this one, ethylamine, which is this one, and then this is phenylamine, right? So this is A, butylamine is B, this is C, and this is D. So out of all of them, which one is the weakest base? Now, the concept is that for it to be the weakest, that means so bases do what? They accept protons, right? So protons will be accepted via dative bond. This dative bond, so the electrons are provided by the nitrogen atom, right? Always the electrons will be provided by the nitrogen atom. Now, among them, which of the nitrogen atom, like which of the lone pairs of nitrogen atom is the least available to produce or to become a bond, a dative bond? So here this is a neutral. This could be considered as a neutral one, because here we have two lone pairs, and easily an H plus can attack this and form a dative covalent bond. But here for ethylamine, we already know that this carbon chain is a electron donating, right? This carbon chain is electron donating, therefore it will donate some of its electrons to this to this nitrogen atom, and therefore what happens? The electron density increases, right? Electron density increases on this nitrogen atom. Therefore, it is much easier for a proton to attack this this lone pair and form a dative covalent bond. Therefore, we must say that in this ethylamine is much more stronger base than NH3, right? So we don't have any work with the strongest, we just need the weakest. Now similarly for butylamine, there are 4 carbon chains. That means this carbon chain is more capable of donating electrons than ethylamine. That means butylamine is a more stronger base than ethylamine, right? But we need the weakest. So here we have phenylamine, where this lone pairs actually overlaps with this delocalized electrons here in the benzene ring, and since they overlap, so the nitrogen is less capable of providing its lone pairs to a proton. That means this since nitrogen is not as much capable as this ammonia or this butylamine or ethylamine, that means this will be a weaker base, since a H plus ion will not be able to attack this lone pair as easily as this 3, right? So we have the weakest base as phenylamine. Always remember that wherever we have the benzene ring, the bonded atom or the bonded molecule always becomes less available to be to form any bonds because of this delocalized delocalized electrons. Moving on to the next question, we have this type of question where stoichiometric question, where it says that a 10 cubic centimeter mixture of methane and argon is ignited. The methane requires 4 cubic centimeter of oxygen for complete combustion. What is the volume of argon in cubic centimeter in the mixture? Okay, so we have in total 10 cubic centimeter, which contains both methane and argon. So if we do the combustion of methane, so this is our equation. So we can see that the mole ratio for methane and oxygen is 1:2, right? That means, so 1 mole of methane will react with 2 moles of oxygen, and so for this we know that we can replace the amount of moles with the volume. So we can say that 1 cubic centimeter of methane produces 2 cubic centimeter of oxygen. So by that ratio, for 4 cubic centimeter of oxygen, we will require 2 cubic centimeter of methane. So we already know that we have 2 cubic centimeter of methane. That means the rest of this 10 cubic centimeter is argon, right? Therefore 10 minus 2 is 8. Therefore we have 8 cubic centimeter of argon. This type of question is frequently found in the question paper, so revise them. Moving to the next question, when 10 cubic centimeter of butene C4H8 is ignited with excess oxygen, there is an overall decrease in volume of X. Okay, so the overall volume decreases after the end of the reaction, and we say this is the given equation, and then it says that a further decrease in Y cubic centimeter takes place on the addition of aqueous sodium hydroxide as carbon dioxide is removed. So sodium hydroxide removes the carbon dioxide produced, right? So the volume of carbon dioxide is Y cubic centimeter. Now we can clearly see from this mole ratio that 10 cubic centimeter of butene will react with 60 cubic centimeter, since the mole ratio is 1:6. Therefore 60 cubic centimeter of oxygen is reacted with it, and 40 cubic centimeter of carbon dioxide is produced. Since Y was the volume of carbon dioxide, it means the value of Y will be 40. So the value of Y will be 40, right? So we are left with it's either option A or option C. Now for the value of X, it says that the overall decrease of the volume was X cubic centimeter. So initially we had how much? We had 10 cubic centimeter of butene and 60 cubic centimeter of oxygen. So we had this as the initial value, initial amount, and then 40 cubic centimeter of carbon dioxide was removed, right? 40 cubic centimeter of carbon dioxide was removed, and so therefore this is the overall decrease in the volume, which is x. Therefore x is, this is 70 minus 40 is 30, therefore the value of x is 30. That means our correct option is A. Then we have another question that on the electrode potentials. So the standard electrode potential for two half cells are this, and then explain in terms of electrode potentials why acidified dichromate ions react with concentrated hydrochloric acid to form chlorine, even though the E cell value is negative. We know that if E cell value is negative, then the reaction is not feasible, whereas if the E cell value is positive, the reaction is feasible. So the explanation would be that the concentration, increasing the concentration of hydrochloric acid actually increases the concentration of H plus ions, and therefore if the concentration of H plus ions increases, this equilibrium will shift to the right hand side, right? It will shift to right hand side. So if this shifts to right hand side, the E value, right, the E value increases, right? It will increase by a few amounts, so it increases from 1.33 to 1.34 to 1.35 like this, and so on. And so HCl has H plus and Cl minus. Therefore, we already know that the concentration of Cl minus is also increasing. If this increases, this reaction will actually shift to the left hand side. The equilibrium will shift to left hand side. That means this value will keep decreasing. So at one point, at some point, we'll see that this value overtakes this value. That means this value becomes less than this value, and therefore at some point the E cell value becomes positive. Okay, since this is very small, the E cell value is very small, therefore at some point increase in the concentration will give rise to the E cell value to will cause the E cell value to be positive, and so the reaction is thus feasible. Moving on to the next question. This is a really easy question. So we have to find the empirical formula of a compound. We are given the percentage amounts of potassium, iron, and oxygen. You already know how to find out the empirical formula. So we first divide the percentages with the AR of the atomic mass of the elements. So this is the first step, is divide by the relative atomic mass, and then we find out that which of the ratios is the smallest, and we divide it with the smallest ratio. So here we can see that the smallest ratio is 0.5, and so we divide each term with 0.5, divide by 0.5, and we get 2, 1, and 4. That means our required empirical formula is K2FeO4. Next, we have question B. The reaction between iodide ions and persulfate ions is thermodynamically feasible under standard conditions. The reaction is very slow, but is catalyzed by the presence of Fe2 plus ions. We have done this before in question 1. So give a reason why the activation energy is high. So the activation energy is high because both of them are negative ions, and so they repel each other. Since they repel each other, therefore we'll need a more energy for them to react together. Okay, then we are asked to write the ionic equation. So the ionic equation will be that S2O8 minus will react with Fe2 plus, forming Fe3 plus ions, and then this Fe3 plus will later be oxidized by these iodine ions to form iodine and Fe2 plus. So here we get Here we get Fe2. The Fe2 plus is this is oxidized. Here Fe2 plus is oxidized, and here it's reduced. Fe3 plus is reduced to Fe2 plus. Okay, next, moving on. In aqueous solution, iron 2 exists as the complex ion Fe(H2O6). Then explain how water acts as a monomer ligand. Okay, so water, the oxygen atom in water, so we know that water is like this. This is H, this is H, and this is O. So O actually has 2 lone pairs. Now one of these lone pairs can be donated to the Fe2 plus ion. This one of the lone pairs of this oxygen atom forms a dative covalent bond with the Fe2 plus ion, and therefore since one dative covalent bond is formed, so this is a monomer ligand, and a complex ion is formed with 6 H2 6 water molecules. This is because Fe has a coordination number of +6. Okay, explain the shape of FeH2O6 complex ion. Okay, so we see that we have 6 water molecules. That means the therefore we already know that the shape of the complex ion will be octahedral. And why? Because there are 6 bonds, right? So Fe is bonded with 6, 1 2 3 4 5 6. So 6 bonds. They will try to be in such a way that they are in a three-dimensional way, in such a way that the repulsion between these pairs, this bond, the repulsion between these bonds is the minimal. Okay, so in order to do that, they have a such a shape that we call it, and that shape is called octahedral. Number 9, a dipeptide has the molecular formula of this, and the dipeptide is hydrolyzed to form 2 amino acids. One of the amino acids produced does not have a chiral center. What is the structure of the other amino acid which does have a chiral center? Okay, so there are a lot of questions which are asked on chiral center. So what is a chiral center? A chiral center is a central atom that has 4 different types of groups, or 4 different kinds of groups attached to its 4 bonds. So there will be a carbon, and therefore there will be one type of group, a separate 4 separate groups attached to this carbon atom. There will be no repetitions, right? So here we have 7 carbon atoms. A dipeptide is 7 carbon atoms. That means it's like this: 1 2 3 4 5 6 7 carbon atoms. Now if we just split it into 2 amino acids, one which doesn't have a chiral center, we can see that we can split it into these 2, right? So COOH, NH2 and H2, and this one. So one will have 2 carbon atoms, and the other therefore will have 5 carbon atoms. So 5 carbon atoms, and how many hydrogens? So we can see that 1 2 3 4 5 6 and 7. So we have 5 carbon atoms and 7 hydrogen atoms, right? So any configuration here that has 5 carbon atoms and 1 hydrogen atoms, along with a COOH, along with a carboxylic acid group and a amine group, will be our required answer. So here we see that option A has a sulfur in it, but we didn't have any sulfur here in the molecular formula. It means A is not our answer. For B, we have 1 2 3 4 5. Okay, we have 5 carbon atoms. Let's count the hydrogen atoms. So here we have 1 2 3 4 5 6, and then we have 7, right? Am I doing that? 7, and here we have 8. So we have 1 extra hydrogen atom. That means B is not our answer. Let's look at number C. We have 1 2 3 4 5 carbon atoms, and let's count the hydrogens. There will be 1 2 3 4 5 6 and 7, and here we don't have any hydrogen. So in total we have 7 hydrogen atoms, excluding the NH and COOH. Therefore our answer is C, because here in D we have how many carbon atoms? 1 2 3 4 5 6 carbon atoms. We don't have 6 carbon, we need 5 carbon atoms, right? So C will be our answer. Moving on to the next question. Transition metal compounds can show a number of different types of isomerism. Hydration isomerism is where different numbers of water molecules act as ligands. Okay, blah blah blah. Then we see that anhydrous chromium chloride is a valid solid which can react with water to produce 3 isomers. Okay, so we have 3 isomers here. So one is here, one is this, one is this, and one is this. So if you look closely here, we can see that these 3 are different, and these 3 different ligands give 3 different colors. So we have to explain why these 3 isomers have different colors. So these 3 have 3 different ligands. Here the ligand is what? Here the ligand is only H2O, but here the ligand is 5H2O and 1 Cl, and here we have 2 chlorine and 4 H2O. So they have 3 different ligands. 3 different ligands means there will be different energy gaps between the d orbitals, right? We already know that why does transitional elements give color? They give color because there will when a complex ion is formed, the d orbital is split into two orbitals, which is like a higher energy orbital and a lower energy orbital. This will be a low energy orbital, and this will be a high energy orbital, and the d orbital splits into these two. And so electrons from the low orbital actually gains photons, like they absorb the photons from light and gain enough energy to move on to the high energy orbital, and then they don't stay there. They radiate some of the energy and come down to this low orbital. This revolvement of these electrons keeps on happening. So they first absorb photons to move to the higher energy orbital, and then radiate some energy to come down to the low energy orbital, and the radiated energy actually gives off the color that we see. So since for these three different ligands, we have different energy gaps between this low and high energy orbital. So therefore, different wavelength of photons will actually be absorbed. So different wavelengths of photons is absorbed for this electron to move to the high energy orbital. That means we will see different wavelengths of light. So different wavelengths of lights means different colors. Moving on to the next question. This question is about benzene. Okay, so here you'll be asked to show the reaction mechanism. Okay, for maybe addition of bromine with benzene, or like it could be bromine, it could be NO2, it could be any other, it could be chlorine, right? So you have to just show the reaction mechanism. So at first, what happens that this bromine is attacked by this benzene. What do you say? The delocalized ring. So the electrons from this ring actually attracts this bromine, and this bromine then later forms a bond, starts to form a bond with this carbon, and therefore, since it was a positive, that means it lacked an electron. So this whole intermediate will become a positively charged intermediate with this carbon lacking one electron, right? Because why does it lack one electron? Because it gave its electron to the bromine, and so previously it had like 4 electrons, and now it has 1 less electron. So this lacking electron will actually be replenished by this hydrogen. So this hydrogen, the bond that this hydrogen shares with this carbon atom, this hydrogen breaks the bond and gives this electron to the intermediate, and the hydrogen breaks free. Hydrogen loses the electron, this hydrogen loses the electron and gives it to the benzene ring, and so the benzene ring is reformed along with the Br attached, the bromine attached to this carbon atom, and H plus is broke free. Next we have NMR. So polyethanol is made from a polymer intermediate rather than by polymerization, as ethanol is unstable. The polymer intermediate is prepared from a monomer X, and this 1 mole of X is burned in excess oxygen, and this gives off 95.6 cubic decimeter of carbon dioxide and 54.1 gram of water. So from here we can calculate the amount of moles. So since we have 95.6 cubic decimeter divided by 24, we get 4 moles of carbon dioxide, and from here this mass of water we can get like 54.1 divided by 18 is 3, so we have 3 moles of water. So from here, since there are 4 moles of carbon dioxide, it means there are 4 carbon atoms, and since there will be 3 moles of water, that means in total we have 3 to the 6 hydrogen atoms. So we have 4 carbon atoms and 6 hydrogen atoms. Now we look at the infrared spectrum of the monomer. Now we can see that there are spikes, this P and Q. This Q is at a mark of around 1650, and the P is around at a mark of 1730. Now if you look at the data table that you'll be given from the data booklet, you'll see that the 1650 mark actually refers to an alkene, and the 1730 mark actually refers, like this is 1735 to 1750, refers to an ester, right? An ester. So we have an ester and an alkene. So if we just think about it, logically, so we have an ester group, this is ester group, right? And we'll have an alkene. So this is an ester, and then this ester is bonded with an alkene. This is the required alkene, right? And we needed 4 carbon atoms. So here we have 1, 2, 3, 4 carbon atoms, right? 4 carbon atoms, and in total we need 6 hydrogen atoms. So here we have CH3, 3, 4, 5, 6. So we have 6 hydrogen atoms. We have to just think a little bit critically for this question. Okay, think a little bit critically for this question. So we will have an ester, and this ester must be bonded with such a carbon atom which will have an alkene, so which will have a double bond. So we did this, we connected this, we bonded this carbon atom with a double bond. So we have CH2, and this is we have this carbon atom already has 3 bonds, so therefore 1 bond is free, therefore it has one hydrogen, and we are left with, so we already used 3 out of 4 of our carbon atoms, so there will be another CH3 here bonded with the CO. Next question, we have titration type of maths. So potassium dichromate oxidizes iron 2 ions to iron 3 ions in acid solution. This is the given reaction formula. So iron 3 ions doesn't react with potassium dichromate. Okay, this ions will not react with this, therefore we are safe. Only Fe2 plus ions will react with the dichromate ion. Okay, a solution Y contains 6.28 gram of iron as a mixture of iron 2 ions and iron 3 ions. Right, so in 1 cubic decimeter, the mass of this mixture is 6.28 gram. Now 50 cubic centimeter of sulfuric acid is added to 25 cubic centimeter. So from here we took, from this 1 cubic decimeter, we took 25 cubic centimeter of Y, and we titrated this with a solution of 2.56 gram per cubic decimeter of dichromate ions. Now this titration is repeated, and then we see that the mean titrate was 22.55 cubic centimeters. Okay, so we are given the concentration in mass of the dichromate ion, so we can find the concentration in moles. So 2.56 divided by the mR of Cr2O7, which is 216, we get this is the mole, this is the concentration. So we have the concentration in mole per cubic decimeter, right? In mole per cubic decimeter, the concentration of Cr2O7. From here we can find out the mole, so the concentration times volume, we did this, and this is the mole of Cr2O7 of the dichromate ions. So from the equation we see that the mole ratio of dichromate ions and Fe2 plus ions is 1:6. Therefore the mole of Fe2 plus ions will be the 6 times the mole of dichromate ions. That means 2.67 into 10 to the power minus 4 times 6, which gives us this value. And therefore this is the mole of iron 2 plus in what? In 25 cubic decimeters. But we need the mole of iron in 1 cubic decimeter. So 1 cubic decimeter is 1000 cubic centimeters, right? So divided by 25 we get 40. So that means the mole of iron 2 plus in 1 cubic decimeter will be 40 times the mole that we found in 25 cubic decimeters. So we just do that. So mole in 1 cubic decimeter is this value times 40, which is 0.064, and from here we can find out the mass. Mass is mole times the molecular mass, which is for iron, which is 56, and this is the gram. So 3.584 grams of iron. What? Iron 2 plus. Now if we need to, since they asked us to find the percentage of iron 2 plus, we just subtract this value that we found from what we had earlier for Y. So 6.28 minus 3.584 divided by the total amount into 100 gives us 42.9%. And next, and this is our last question, the aroma of strawberries is due to a number of volatile compounds, including the 4 isomeric esters shown. Okay, so we have 4 esters. Now they asked us which of the esters have 5 peaks in their carbon-13 NMR spectrum. Okay, so carbon-13 NMR spectrum gives peaks for what? For different carbon environments, right? If you remember correctly, they give this peaks for different C environments. Now if we look at this esters, we see that for P, this is one carbon, this carbon is, this 2 carbon is different from this 1 and 3, so this is a different carbon environment, this is different, this is different, this is different, and this is different. So we have in total 6 different carbon environments. That means the peaks that will be shown will be 6 peaks. So here it will be 6 peaks. For ester Q is the same, there will be 6 peaks, so 1 2 3 4 5 6. But if you look at R, you see that this carbon, this 2 carbon is bonded with 2 CH3 groups, right? So both of these CH3 are actually have the same carbon environment, because both of them are connected to 1 carbon. So both of them are connected to this carbon, right? Both of them are connected to this carbon, so they both have the same environment. That means they are similar. Therefore this is 1 2 3 4 5. So in total we have 5 different carbon environments. That means we will get 5 picks for R. And similarly for S, we have this again, both of these methyl groups CH3 have the similar carbon environments. That means in total we have 5 different carbon environments. That means only ester R and S will give 5 picks. Then which of the esters will not have a doublet in its high resolution porphyrin NMR? So we know from the n+1 rule that what is n? N is, so the carbon that we are for the carbon that we are calculating. So we have to know that the neighboring carbon, the amount of hydrogen atoms that is bonded with the neighboring carbon, right? So here we can see that here at Q, in Q we have this is carbon 5, but carbon 5's neighboring carbon is carbon 3, and carbon 3 has one hydrogen bonded to it. And for doublets, since there is one hydrogen bonded to it, by the n+1 rule, so 1 plus 1 will be 2, so this will be a doublet, right? Similarly, we need to find out that which of these compounds have such a neighboring carbon atom which has only one hydrogen bonded to it. So for ester R, we see that here this number 2 carbon has one hydrogen bonded to it, and similarly for ester S, we have this carbon number 4 which has one hydrogen bonded to it. But if we look at ester P, there is no such carbon environment where that carbon has only one hydrogen bonded to it. See, here are 3, here's 2, 2, 2 and 3. No carbon atoms which has one hydrogen bonded to it. That means only P will not give a doublet. The others will give a doublet. So our answer is A. Now last question. Which of these esters could rotate the plane of plane polarized monochromatic light? Okay, so the only type of compounds that can rotate the plane polarized light are optical isomers. So what are optical isomers? Optical isomers have one key feature, that is they have a chiral carbon. What is a chiral carbon? We have discussed this before. A chiral carbon is such a carbon that has 4 different groups bonded to it, right? So here we can see that only Q has a chiral carbon. Which one is it? This one. This carbon is a chiral carbon, because see, this is a CH3, this is CH2CH3, this is a different group, this is a different group, and this is a different group, and the hydrogen is a different group. Therefore this carbon atom has 4 different, not repetitive or similar, 4 entirely different groups or like carbon chains attached to it, right? So only Q has a chiral center, and none of the P, R and S has a chiral center. Therefore our answer is A. Hope you liked the video. These are all my predictions. I'm not sure that these particular questions or this type of questions will come in your exam tomorrow, but these are my predictions that this type of questions are very common for the previous, like I found this in the previous 5 or 6 years questions. Therefore I hope some of them will be common in your exam. So I will advise you to study them more, since this will just boost you at least 7 to 10 marks in your exams. And thank you very much. Welcome students to this revision session. With your exam around the corner, we have prepared a few questions, frequently asked questions that might come in your exam tomorrow. So stay tuned and be sure to revise these things, because these questions might help you to get 7 to 10 marks for the next exam. Okay, explain why complex ions this and this are colored and have different colors. So we know that transition elements, when they form complex ions, give color. But why do they do this? Because their d orbitals split into two different energies. The difference in energy depends on the ligands. Yes, so different ligands will cause the d orbital to split into different energy. So since they split into two different orbitals, one is low energy and one is high energy, so the gap between their energies will actually depend on the ligand. Okay, and then the difference in energy leads to a different frequency and wavelength of photons of light being absorbed. So an electron from the lower energy orbital will actually absorb a photon and gain the energy to go up to the higher energy orbital, and therefore the unabsorbed frequency, so a specific frequency of photon is missing from light, therefore the unobserved frequencies is just reflected, and that is seen as the color of the compound or of the solution. Next, compare and contrast the origin of the color of a copper complex, copper 1 complex, with the origin of the color of the copper 2 complex. Okay, so see, one is Cu plus and one is Cu2 plus. They both have different, so the energy between their splitted d orbital is different, therefore they have different colors. So the difference in energy levels determine the color of the flame and the complex ion. So basically they will have different colors of flame and the solution. Then differences in flame test. So heat energy results in electron promotion. The return of an excited electron to a lower energy state releases light, right? So for the flame test, when we heat, so again the d orbital is splitted between two energy orbitals. So when we heat it, the electron gains energy and moves up to the high energy orbital, but it doesn't stay there. After some time, it again comes down to the lower energy orbital, and then when it comes down, it releases energy, and the energy that is released during that state is the light that we see. Now, for complex ion, why there is a difference in their complex ions is because of the splitting of the d orbitals. The d orbitals split into two right here, and the energy gap between them. The energy gap between them depends on the ligand, right? So light energy so different amount of light energy or different frequencies of photons will be absorbed, and therefore different colors will be seen. Next, compare and contrast the complex ions formed by cobalt 3 with the ligand ethane 1,2-diamine and with the ligand EDTA 4-. Okay, so the similarities between these two ligands is that both ligands do form dative covalent bonds, right? Do form dative covalent bonds with cobalt 3 ion, and both have a coordination number of 6, and both will have a shape. Since their coordination number is 6, both will have a shape of octahedral. Now the difference is that EDTA4- is a hexadentate. Hexadentate means that it can form one compound. So one molecule of EDTA4- has what? Has 4- has 6 sides. Like it can form. Okay, let me rewrite. One molecule of EDTA can form 4. Not 4. Can form what? 6 dative bonds, right? That is what hexadentate means. And while ethane 1,2-diamine is bidentate, that means it can form 2 dative bonds. Okay, the complex with EDTA4- will be negatively charged. Yes, EDTA4- is negative, while ethane 1,2-diamine is neutral. That means the total charge of the complex will be positive, and the complex of EDTA4- is more stable than the complex with ethane 1,2-diamine, because there is an increase in entropy. Okay. Next, cobalt 2 ions combine with substances in solution to form complex ions with different coordination number. Right? So what does it say? The cobalt 2 ions combine with substances in solution to form complex ions with different coordination numbers. Discuss the statement by referring to two complex ions containing CO2 plus. So two examples are that cobalt with water as ligands. This has the color of pink, while cobalt with chlorine as ligands has a color of blue. Now the key points are that a ligand. What is a ligand? A ligand is an atom or molecule or any species which is dative covalently bonded to a central metal ion, right? So here H2O and here Cl, chlorine, are ligands because this water molecule and this chlorine molecule are datively covalently bonded. Okay, so datively covalent bond means that the cobalt this means that the water or the chlorine are solely providing the two electrons needed for the bond. So both of them are dative covalently bonded, and the coordination number is the number of dative covalent bond to a central metal ion. It means that coordination number means that the central atom, which is cobalt here, the number of dative covalent bonds that the cobalt can form is the coordination number for cobalt. Now, here it says that cobalt with the water as ligands shows 6 water molecules as ligands forming bonds with cobalt, leading to a coordination number of 6, whereas cobalt COCl42- shows 4 chloride ions as ligands. Chloride ions are large and only fit 4 around the metal ion, right? So here cobalt still has a coordination number of 6, but the thing is that only 4 chlorine atoms can fit in around the molecule. So cobalt is really small compared to chlorine. So chlorine, only 4 chlorine can attach. Okay, no more than 4. That is why CO there is only 4 dative covalent bonds. Now state 3 reasons why TMS is suitable for use as a standard when recording NMR spectra. Okay, TMS is a compound, and TMS is used because it is inert and non-toxic. The peak doesn't overlap with other peaks. Okay, so and they usually almost always give single peaks. It has a low boiling temperature and can be easily removed, and it also is volatile, and it gives a strong signal. So only a small amount of TMS is needed. Next, give the steps to show that 2,4-dinitrophenylhydrazine could be used to distinguish between carbonyl compounds. So we already know that to distinguish between carbonyl compounds, for example, like from aldehydes to ketones, to distinguish them, 2,4-dinitrophenylhydrazine is used. And why? Because reacting with an aldehyde, 2,4-dinitrophenylhydrazine will give an orange precipitate. And then how can we identify that which compound is that? Then what can we do? We can filter and then recrystallize the product that we have that gave the orange precipitate, and then we can determine the melting temperature. So from this melting temperature, we can then identify that from the database values that which compound are we are we testing. Next, catalytic converters of car exhaust systems have a honeycomb structure. Explain why. Okay, so they have honeycomb because to increase the surface area, and the more the surface area, the more the active sites, and therefore the more reactions can occur, and also allows gases to flow through the exhaust. Give 2 reasons why different amino acids have different RF values. Okay, so amino acids have different amino acids will have different solubility, right? Different solubility to the stationary phase, and amino acids have different solubility in the mobile phase. Okay, so next, explain why different compounds will have different retention times in the same column under the same conditions. So retention time actually depends on the polarity or the attraction of the component for the stationary phase, and therefore the greater the attraction of any component for the stationary phase, the greater will be the retention time. Explain how impurities in gaseous reactants could make a heterogeneous catalyst less effective. Okay, so impurities absorb into the catalyst surface and occupy the active sides okay, so basically it says that the impurities that are present in the gaseous reactant, they adsorb into the surface of the catalyst, and this prevents bond weakening in the reactants. So these impurities reduce the surface area of the active sites that are available for reaction, and therefore by doing so impurities may form strong bond or be less likely to dissolve. So basically these impurities in place of the actual reactants that you want to get absorbed and weaken their bonds, these impurities can form strong bonds with the catalyst, and therefore they will be it will be harder to dissolve them, right? So basically these impurities are causing are reducing the capability of the catalyst to catalyze the reaction. Okay, LiLH4 is a source of hydride. Give a possible reason why LiLH4 cannot be used to reduce alkanes. Okay, this is because the hydride ion, this hydride H minus ion, will not attack and will be repelled by the region of high electron density, right? So basically alkenes have double bonds, right? So there is high electron density here, and therefore since this is also negative, this hydride ion will be repelled by the electrons. Suggest why 2-nitrophenol is less soluble in water than 4-nitrophenol. Okay, so 2-nitrophenol forms intermolecular hydrogen bonding, right? Intermolecular means in between the same molecule they form hydrogen bonding, and 4-nitrophenol only forms intermolecular hydrogen bonding. So intermolecular means between two separate molecules, right? Between two separate molecules. For example, this is one phenol, this is one phenol, and this is another phenol, right? So if hydrogen bonding is formed between these two compounds, between these two molecules, then it is intermolecular. Whereas intramolecular means between the same compound. If this was like this, that in between the same compound, here is an OH and then something something something, and then here is another OH, and hydrogen bonding is formed in between the same molecule, and it is called intramolecular. So 2-nitrophenol shows intramolecular hydrogen bonding, whereas 4-nitrophenol forms intermolecular hydrogen bonding. Therefore the hydrogen in 2-nitrophenol cannot form hydrogen bonds with water because they already have hydrogen bonding between its own molecule, between its own bonds. Explain why it is difficult to produce a pure sample of 2-chloropropane when chlorine reacts with propane. Okay, so the chlorine radical can remove a hydrogen atom from anywhere in the propane molecule. As a result, a mixture of products is formed. Yes, so it is really difficult to produce a pure sample because that chlorine molecule in the propane molecule, so propane is like this, right? Here everything is H. So the chlorine can actually attack any of the carbons at any position. So we don't surely know that the chlorine will be which hydrogen which hydrogen atom the chlorine will substitute. Therefore a mixture of products will be formed. The chlorine could be here, chlorine could be here, the chlorine could be here, it depends. Therefore a mixture of the chlorine of the compound will be formed, and the pure sample is very, very hard to produce like this in this reaction. Okay, then next question. Halogenoalkane reacts with OH minus ions. Yes, hydroxide ions. So reaction 1 is shown here, and reaction 2. Okay, so explain the optical activity of the product for reaction 1 and reaction 2. So in reaction 1, reaction 1 forms an optically active product as only one enantiomer is formed. Yes, this is only one enantiomer. This happens because the hydroxide ion can only attack on the opposite side of the leaving group, and this causes inversion of configuration at the chiral center, and therefore reaction 2 product mixture shows no significant optical activity as a racemic mixture forms, right? Then we have the intermediate is a planar carbocation. This allows the hydroxide ion to attack from either side of the plane. Or reaction 2 produces a racemic mixture, so the product is not significantly optically active. As a result, reaction 2 is SN1, and the two products rotate the plane of polarization of plane polarized light in opposite directions. So basically this is an optically active, where does it say? This is optically active, and so is this. Therefore they both have a chiral center, and they can rotate the plane polarized light in opposite directions. Next, describe how the orbitals from C atoms form bonds in benzene. So there is a head-on overlap between orbitals from neighboring C atoms to form a sigma bond. The sigma bond is formed due to this type of bonding. So this is a p orbital, and this is another p orbital, right? So overlapping between these two causes sigma bond, but the remaining p orbitals overlap sideways. So the remaining p, for example in C, the pz orbital like this overlap like this in sideways. So since they overlap sideways, they are called pi bonds. So this causes this pi bond. So they can actually be shown like this. Say this is C, and this is the electron cloud for a pi bond. This is a pi bond, right? So therefore, the electrons in the pi bonds are delocalized around a ring of. So since benzene has a cyclic structure, so the pi electrons can delocalize above and below the carbon atoms, and therefore the benzene molecule or the benzene ring is formed. Explain why transplatin is not effective in the treatment of cancer. So trans isomers have two chloride ions opposite to each other. This gives the isomer the incorrect shape to cross-link the DNA strands. You just have to memorize this few stuffs. BrO3 minus plus 5Br minus plus 6H plus produces bromine and water. Is this so the question is this disproportionation or not? This is not disproportionation, because for disproportionation the condition is that from one reactant two separate products will form with different different oxidation states. So one will increase on one the oxidation state of one product will increase while the oxidation state of another product will decrease. But here if you see that the oxidation number of bromine is +5 in here, so here it's +5, and -1 in here, right? This is -1, but here it's 0. So they both, one is being oxidized, one is being reduced. That's okay, but these are two different species of bromine. Therefore, this cannot be a disproportionation. If it had happened from only one species of bromine, then it was okay. So for the condition for disproportionation is that oxidation and reduction both will need to happen from only one species of reactant. Comment on the fact that N triple bond N is weaker than phosphorus triple bonded with phosphorus. Okay, so this is because initially we know that the N nitrogen triple bond is actually stronger than phosphorus triple bond. However, in the nitrogen triple bond, the lone pairs of electrons of nitrogen atom are close to one another, right? So for nitrogen here there are lone pairs, right? So they are very close to one another, and this leads to significant repulsion, and which weakens the bond. In both nitrogen triple bond and phosphorus triple bonds, the lone pairs are positioned at the ends of the molecule at 180 degrees, just like this, to the bond, so the repulsion between lone pairs is less significant. The pi bonds in nitrogen are considerably stronger because of more effective sideways overlap between the two p orbitals of nitrogen atoms. Explain why cisplatin is dissolved in a dilute solution of NaCl when used as a medicine instead of keeping it in aqueous solution. This is because to prevent the chloride ions in the cisplatin leaving and being replaced by water molecules before cisplatin enters cells. Okay, so we need cisplatin. If the chloride ions were to leave before they enter the cell, then the medicine would not be effective. Okay, thank you students. This is the end of the video. For keep tuning along with the video. I hope you good luck for the exam tomorrow. I hope that this video will help you revise and answer some very frequently asked questions. Thank you.